Okay, welcome everyone to this week's CDAC sponsored webinar talk. I think on this day of anxiety, perhaps everyone needs to kick back and relax and think about the quest for a novel periodic table under pressure. So to that end, I'm pleased to introduce one of our colleagues, Ellis Stavrou from Livermore. Ellis received his PhD from the National Technical University of Athens, Greece. He was a postdoc at the Max Planck Institute for Solid State Research and then moved to the Carnegie Institution, where he worked on a variety of problems that were sponsored by CDAC in CDAC labs, and where I got to know him. He then moved to Livermore and joined as a staff scientist in 2014. Ellis's work spans a broad area of high pressure, and he's worked on a variety of problems. And as he likes to say, he uses high pressure to break the boundary of conventional chemistry, physics, and material science to make new materials, which is clearly the topic of today's talk. So welcome, Ellis. We're looking forward to it.
Okay, thank you for the introduction. Thank you for the invitation. And also, I think we should all thank CDAC for organizing this series of talks that not only give us the opportunity to present our results, but also communicate during this challenging time. The title of my talk, I understand that it's very broad, is the quest of a novel periodic table under pressure. What I would like to imply or convey here is that we are trying to understand the chemical properties of elements and compounds under pressure. And this is a relatively new field. A lot of groups are working in this direction. I'm also happy that I see a lot of collaborators and people that are working also in this direction attending this talk. As you may know, one of the most hot topics in this field is the superhydrides. I will not say a lot about this topic. A lot of experts, including Russ, is present here. I will just remind an old study that we have done, and we are all aware about recent news about record disease. So I will try to avoid a lot of technical details, especially since at least the last talks that I attended, I think they convey the details about experimental techniques and so on. I will try to present a lot of results, and all of them are published. I will try to focus more on understanding what we know up to now about how things change under pressure. So in general, when I start presenting this kind of talk, for some reason, okay, in a general audience, I'm trying to convince them that, okay, you may don't see high pressure, high temperature in everyday life, but 90% of matter is under these conditions. And there are a lot of reasons that we are interested about how things are under high pressure and high temperature. This interest stems from academic curiosity, like, let's say, solve mysteries and paradoxes. And I will dedicate some time in the talk to discuss these issues. Also, something very interesting, to synthesize novel materials with new properties like super hardness, super conductivity, and high energy density. But also because these conditions exist in geoscience, but also under detonation conditions. And in Lawrence Livermore, we have done a lot of work under detonation conditions with a recent paper published about the response of graphite under detonation conditions. So I will just introduce the main problems that we have in this field. And the main problem is that we are trying to synthesize a new compound under pressure. And at the beginning, you don't really know exactly what exactly will be the characteristics of this compound. And at ambient conditions, for the chemical ordering, we have the periodic table. Okay, even a high school student more or less can at least predict for simple elements how the chemical bonding will be by just looking on the position of an element in the periodic table, like let's say anionic bonding or covalent or metallic. The main problem is when things come to the long-range order, to the crystal structure of a compound. In this case, the prediction is not straightforward, and the main problem is that you need huge computational power to predict the crystal structure. And here I just pick one funny paper saying that no, the crystal structure is not predictable. And the reason that I'm discussing the structure is that not everything, but almost everything about the material, properties, and so on, can be determined by knowing its crystal structure. And also with X-ray diffraction, usually the first info we get when we synthesize a new compound is the crystal structure. However, the last years, and I think all experimentalists, we are grateful on all this theoretical effort, there are some new tools that they allow us to kind of predict the crystal structure of compounds with these new crystal structure search algorithms. And in reality, the main tool that we use, or at least the main tool that we get from theory to guide our experiments and results, is the convex hull. I introduced the convex hull because I will use it a lot in the talk. And in reality, this is a graphical way to present the stable stoichiometries of a system, ternary or binary or ternary, at a given thermodynamic condition. So it says to us what we expect at a given pressure. And convex hull, the stable stoichiometries in reality, changes under pressure. And it might be simply like this, let's say in this case of sodium and helium, that I will present some results of the compound, or it might be extremely complicated, as in the case of a lithium and a phosphorus. But at least we'll have an idea about what kind of compounds we expect to be stable under extreme thermodynamic conditions. So what exactly is happening here? What exactly is happening when we increase the pressure on a system? It looks like that the periodic table or the rules that we know are not valid anymore, at least not at the extent that they are at ambient conditions. And the reason is that the energy we transfer through pressure to the system is comparable with the bond energy. So we change in reality the energy landscape. And usually, again, when I give this talk to general audience, I'm trying to make the parallel with the classical mechanics, that it is okay for normal conditions. But then when you start to apply classical mechanics to things like large objects and so on, you need new theories. So this is why we can kind of access novel stoichiometries, because we change the bonding. Usually, and I think this is something well known in the field, one of the main problems is that we need to overcome energy barriers for chemical transformation. Here I just show a very simple example of diamond and graphite. At ambient conditions, you have the sp2 as stable configuration. You go to high pressure, you need some temperature to overcome the barrier. And then the trick, if we like, and what we are trying to do here is to have materials that they are quenched, which means metastable at ambient conditions. And the idea is that when you release the pressure, the energy landscape returns back to the stable one at ambient, but due to the inverse barrier, the system may be trapped. And this is more or less why the diamonds are forever. So I would say at the beginning, there were a lot of examples of elements that completely change the chemical properties or the bonding under pressure. Some well-known examples, like let's say the synthesis of single-bonded form of nitrogen, 2005, instead of the covalent molecular type of nitrogen, you have an extended solid, or the insulating sodium, at about 200 GPa, if I remember, which forms an ionic solid, which in reality is an electrolyte, and also some recent examples about metallic hydrogen. So the idea here is that if simple elements can show different properties under pressure, So maybe we can go a step further and apply this new, let's say, chemical rules in compounds. And the wish list here is the following. We are trying to have metastable compounds at ambient conditions, aiming to applications if possible. Like, let's say, the case of diamond, which is a very well-known example. Ideally, you would like to have synthesis at low pressure and low temperature to achieve mass production, and also to tailor the properties like superhardness, energy density, and so on. I think we should all think about pushing this field towards practical applications. And I think this is the way forward in order to attract more interest in this field. So just to start, I will give you an old example about what exactly we are meaning about new stoichiometries and so on. This is a relatively old paper now from Science 2013. And we deal with a very simple system, rock salt, sodium chloride. So if you just take sodium chloride and you apply pressure, you will see a phase transition at about 25 GPa, which nowadays is kind of trivial. Now the idea is, can we think beyond textbook chemistry? Can we think about if it's possible to have stoichiometries beyond what the periodic table says, the one-to-one? And looks like, at least from the theoretical point of view, even at very low pressures, 20 GPa, stoichiometries which are rich in sodium or chlorine become stable. Again, you can see the convex rule here that I discussed before. Of course, this is amazing to be true before you perform experiments. And indeed, we have performed experiments and we managed to synthesize both families of compounds, both the chlorine-rich and the sodium-rich, at about 50 GPa and after laser heating to 2000 Kelvin. And now, I don't know, I mean, I think Maduri is attending the talk, so he may want to comment. I will speak for myself, but I will say that, in my opinion, this was amazing, very good result, but more or less academic curiosity. I was never expecting some practical applications. And although we made the comment that we see something like a two-dimensional electrical conductivity, I don't know if it is clear here, but there are kind of layers of sodium that they are conductive and layers of chlorine and sodium that should not be conductive. I was not expecting some practical applications, and it looks like I was wrong, and I'm very happy that I was wrong. Because before 2 years, a different group using conventional chemical approaches, they managed to synthesize these compounds at ambient conditions, and exactly they discussed this two-dimensional conductivity. And you may see here how they compare what they managed to synthesize on top of graphene surfaces with what we found under pressure. So the reason that I'm discussing this is to make the point that with pressure, it's not only that we can access novel stoichiometries and just stay there. I think high pressure has the advantage that it is the optimum way to run ahead, to probe, to find new stoichiometries, and sometimes the community, the field, might come back using conventional techniques and synthesize this kind of compounds. And this is not the only example. I mean, I'm aware also about a study that they managed to form cubic ghost nitrogen at ambient conditions using radiofrequency plasma. So let's have this in mind, that it's not only that we use high pressure to synthesize these materials, it's also to unlock new stoichiometries and understand the chemical bonding. For the next, I would say 10 slides, I would like to discuss a block of results that have to do with the noble gas elements under pressure. And the idea behind that was that if you try to explore how things change under pressure, maybe the gases are the stronghold of the periodic table, so they don't want to react. So let's see if they can react under pressure. The idea here is let's test some noble gases to see what's happening. And at the beginning, we started with helium because one expects that it's the most stable noble gas, and also it's a very good element in the universe. We also looked on xenon, and the main, let's say, motivation was about the well-known missing xenon paradox, and I will explain more in the next slides. But also very recently we expand our studies to argon. So again, these studies are published, so I will just focus on the, let's say, the main results and trying to understand what's happening here. Now, there are compounds with helium and other noble gases such as van der Waals compounds, but in this case, the idea was if we can form stable compounds with real bonding. And again, according to theoretical predictions, at about 110, 120 GPa, there is a compound between helium and sodium, the sodium halide, if you like, that becomes stable. And in this case, the theory predicted a real bonding between these two elements. So again, we see in science this compound at about the thermodynamic conditions predicted, but also we found some very interesting results from the experiments. And here I saw the equation of state. First of all, there was a 5% reduction in the volume of this compound in comparison to the elements, if you do the superposition, which strongly suggests a stable element, a stable compound. But also during the laser heating, we saw that this element was stable even under high temperature conditions, at conditions that sodium usually melts at this pressure. So this indicated that the bonding there is completely different than the sodium. This was also published in Nature Chemistry 2017, if I remember correctly. And now let's try to understand what's happening in this compound, why it's stable and how it's formed. So let's first see the crystal structure of this compound by just looking on sodium and helium. So this is a well-known structure for AB2 compounds, the fluoride structure. However, this structure, as we know, is not very dense and usually is not stable under pressure. Even conventional AB2 compounds, they show phase transition under pressure. So the idea here is why this phase becomes stable at very high pressure. The solution is that in reality, we don't have a bonding just between sodium and helium. We have a multi-center bonding that includes sodium, helium, and localized electrons. So in reality, we have an electrolyte plus some ionic interaction between sodium and helium. It's known that sodium, this is one of the first slides I saw, forms an electrolyte at very high pressure, at about 200 GPa. So part of the story is that helium forced the system towards an electrolyte state. Nevertheless, this was the first compound between helium and stable compound with helium and other element, which we believe that starts this field of helium compounds. And again, helium is very abundant in the universe, so we may think again about how helium exists inside under high pressure. The next example of noble gas element reactivity is, as I mentioned, the xenon paradox. And the idea behind that is that in the atmosphere of Earth and Mars, we don't have the xenon that we expect. There are a lot of scenarios about where exactly xenon is, but the most prominent one was that probably is trapped inside the Earth core. And indeed, before about 6 years, there was a theoretical prediction that predicted that iron and nickel, xenon and iron, and xenon and nickel compounds can be stable at thermodynamic conditions relevant with the Earth's inner core. However, experimental attempts to synthesize these compounds in 2010 were not successful, although the relevant pressures and temperatures were not exactly close to the Earth core. So we said, okay, we have a theoretical prediction, we have a problem here, we have some previous results, let's see what's happening. Of course, we had to increase the pressure much higher. These are the results of our theoretical predictions. You need at least 200 GPa for iron and 150 GPa for nickel. And we managed to synthesize both compounds, xenon iron and xenon and nickel with X-ray and Raman and everything. And this was published in PRL 2018. So, okay, these compounds are stable, but again, let's try to understand why this is happening. Now, one may argue, okay, xenon is a noble gas, but it's not exactly conventional, it's not exactly a classical noble gas. Xenon, together with krypton, of course, there are large atoms, loose electrons, so it's known now more than 60 years that if there is something like a strong electronegative element nearby, like fluorine and oxygen, they form compounds like a xenon difluoride, which is known and also it's even commercially available. I think there are some practical applications like etching. So, okay, I understand xenon can find an electronegative element nearby and electrons will fly, but here we have to deal with iron and nickel. These are not electronegative elements, and these usually would like to give electrons. So it turns out that this is okay, this is true for ambient conditions, but this is not true under these high pressures. And according to electrolocalization function, things are opposite. Under these conditions, electrons, iron attracts electron, to some extent nickel, but not that much, mainly iron, from xenon. So you have a situation that iron, at least in respect with xenon, becomes electronegative and attracts electron. In nickel, the situation is more or less the same, although the transfer is lower. And in the case of nickel, what we really see is a solid solution between nickel and xenon, giving the idea that nickel is more close to something like a noble gas at these conditions, forming a solid solution with another noble gas. So, okay, we understand how these compounds are made stable through a major change in the properties of iron. We understand that xenon forms compound under these conditions, but the question we ask ourselves, and to be honest also from other people that attended this kind of talks, is okay, how xenon end up there? Because at the beginning, the conditions were not 150 GPa or 200 GPa, and also you see the same problem in mass. So this kind of motivates us to see if we can have a real problem, that we have a noble gas that it really can be at the core, at least in this kind of closed thermodynamic conditions. And we turn to argon. This is the story behind argon. So the idea here is the following, the long story short. We know that, again, according to models, I'm sure there are people attending this talk that they know much more than me in this kind of models. Half of the head flow in the Earth comes from the radioactivity right now, and potassium, as you may see here, is one of the main players that they give a heat through radioactivity, and potassium-40 to be exact. And one of the products of the radioactive decay of potassium is argon-40. The other one is calcium. Now, it is known from previous studies back in 2003 or before for the case of nickel, and I will present some results, that potassium has no problem to form compounds with iron and nickel, and I will give some more details in the next slides. So even at 10 GPa, one can form compounds between potassium and iron. So in this case, it makes sense that potassium may exist in the Earth core. And then through the radioactive decay, you have argon. Now, what's happening with this argon? According again with the models, the abundance of argon in a crust, atmosphere, and mantle is much lower than what is expected. Can argon be stable under these conditions. Argon is not like xenon and krypton, it's not so large. So we decided to check this hypothesis, so we aimed on nickel, mainly because we had the result with nickel and xenon. And indeed, at relatively low pressure, 140 GPa at least for this kind of experiments, we managed to synthesize this compound between nickel and argon 1-to-1. It's more or less an FCC structure, which in reality is a solid solution between nickel and argon, well supported by the theoretical results of our study and so on. In this case, the electron transfer is from argon, from nickel to argon. And this material is stable under high temperature, but also when we return back to room temperature, and also stable when we release the pressure up to at least 100 GPa. And also, I think this attracted a lot of attention with the CNE newsletter, asking that this behavior of argon is not very noble. So in this case, we have kind of the complete story that we can solve some mysteries, if you like, or open questions, saying that we have potassium, we know that forms element compounds with iron and nickel, argon is created there and it's trapped there. But I promised to discuss a little bit more about potassium and iron and nickel. So this is what I would like to do next. And this is the next result. So I don't see the chat though, so if there are questions, I will try to respond at the end. So we turned our attention towards potassium and nickel, trying to understand what kind of compounds can form. Now, at ambient conditions, as you may see the convex hull here, there are no stable compounds. In reality, there is no convex hull, to be exact. And the main reason is the large difference in their charge densities. However, and this kind of explanation applies also to the case of iron. Under pressure, we know that there is a transition in the case of potassium S2D transition, so it becomes more like a transition metal. And indeed, if we calculate the convex hull at about 37 GPa, why 37 GPa? Because back in '96, there was a paper by Parker et al. That they report the synthesis of a potassium-nickel compound just above 30 GPa. However, it was not possible to determine the crystal structure. So at about 37 GPa, you may see how many compounds between potassium and nickel become stable, although at ambient nothing is stable. So we went through the procedure of understanding how this compound was synthesized back in '96, the relative ratio between potassium and nickel and so on. And indeed, we managed to completely elucidate the structure of the compound that they formed back then. And this is a monoclinic compound, potassium to nickel. Up here, okay, things looks trivial. However, what is, at least for me, very interesting is that if we calculate the band gap of this compound, looks like that we have something like 0.6 eV gap. So this means that this compound in reality is a semiconductor or an insulator. So this means that you combine two good metals like potassium and nickel, and you end up with something that it is insulating. So now we kind of have the full story about why we can form compounds between potassium and nickel due to the change of character of potassium and so on. So with this slide, I would like to kind of finish this block of results about noble gases, aiming mainly towards this block of academic curiosity that I discussed at the beginning, and highlight how we can understand how different things are under high pressure, and proceed towards some more applied results, high energy density and so on, And as always, we will start with polynitrogen, which was one of the things that we looked in Lawrence Livermore National Lab and also before. So I discussed this paper at the beginning, the formation of single-bonded cubic gauge nitrogen. Excitement when it was discovered, the best energetic material. Here is a diagram that compares the usual detonation pressure of a conventional high explosive, around 30-40 GPa. This is, of course, the calculated detonation pressure of a cubic gauge. Also, the velocity is huge. So it looks like as the best energetic material and also completely green because all the products are in reality molecular nitrogen. However, the main problem here, and this goes back to the discussion about applications, the pressure and temperature needed, more than 100 GPa and 200 Kelvin, is kind of a showstopper for mass production. Also, this material was not quenchable at ambient pressure. If I remember correctly, when we decrease the pressure at about 40 GPa, it returns back to the molecular form. So the idea here is, and this is not far away from the idea of polyhydrides, which Russ knows everything, about including an impurity in the system, trying to kind of facilitate the formation of polynitrogen species, through a binary or ternary compound. And this represents more or less this red bar here, which is, okay, can we decrease a little bit the detonation pressure, even if it is halved, still much higher, but at least be able to synthesize kind of compounds, it's much lower pressure and also to be quenchable. So indeed, the idea here was to start, of course, from azides. Everybody, I think, everybody, okay, 90% of people in this field start from azides, and the cesium pentazolate and mix it with nitrogen. The reason we choose cesium instead of other alkali metal was just practical to kind of help us in the X-ray diffraction. So as you may see in the convex hull, this kind of pentazolates become stable at about 30 GPa. And indeed, by just mixing the azide together with nitrogen, we managed to synthesize this compound at about 40 GPa. After laser heating, of course, and it was highlighted as a cover and internally in the lab as the Lord of the Rings. I think the reason that attracted such attention is not only because of the energy part of the story, but also because the pentazolate was also a long shot kind of molecular species for chemistry, and I think it was the first one, together with a science paper that published at ambient conditions, that reported the stability of this anion. Now, of course, the synthesis was at 40 GPa, so much lower than the cubic gauge. Also, it was not stable at ambient. It was up to 18 GPa, so still not quenched, but much lower than cubic gauge. And I think it is not surprised that other groups jump on it. This is a paper published 1 year after from France, from Dominic. They use lithium, which has the problem with X-rays, but looks like it's better for quenching the material. And they managed to synthesize more or less the same compound with lithium that turned out to be stable at ambient conditions. So now you have a pressure that it is almost accessible by large volume presses, and also it's quenchable at ambient conditions. Of course, more studies are needed, but I think this was a major breakthrough towards making things more applicable for practical applications. The next example that I would like to discuss, and this is a long story with a huge number of papers published, is the field of the superhard materials. And I'm focusing here on the synthesis of carbonhydrides. This study and other 1,000 more studies was triggered by the theoretical predictions in 89 and 96 of these two science papers, predicting that maybe if you form compounds between carbon and nitrogen, you may have compounds that can rival even diamond in hardness and mechanical properties. A lot of studies, the main problem was that precursors were used, which introduced the problem of impurities. In this case, why I like a lot this study is that we went through the hard way to use elements instead of precursors, graphite and nitrogen. So we mix graphite and nitrogen in diamond anvil cell and then laser heated at a given pressure, which created a lot of experimental problems. Laser heating the graphite, we all know what's happening if you don't do some tricks. And indeed, we managed to synthesize the carbonhydride. The surprise was that it was 1-to-1 instead of 3-to-4. And the pressure, of course, and temperature was very high. I don't claim that these things can have practical applications for these synthesis conditions, but I think it can pave the way for other compounds. And I think right now a lot of people discuss about ternary compounds, including boron and so on. What I would like to highlight in this case is that this compound was stable at ambient conditions, and so it was metastable, and this helped us a lot also to perform ADX and nail down the stoichiometry. So although the synthesis conditions are kind of extreme, the metastability, I think this is something that gives us hope to apply this procedure in other materials. You will excuse me, but I will kind of jump very fast the next slide. In any case, we all know that this is a very hot subject in the field with the first results by RMS group about the superconductivity in H2S. The very recent report of the lanthanum hydride by RAS group, very recently also before weeks from Diaz about the room temperature superconductivity. And I think there are also reports, and there is a paper under review by RAS group about the lanthanum and ammonium borane that it has even higher disease. I would just like to remind that I had some involvement in the first study that synthesized the sodium polyhydride, which to my knowledge at least was the first polyhydride published during my time in GL with the support of CDAC and IFRI. So I will jump very fast to the last two topics that I would like to discuss. The first one is also a paper published before 1 year, and it's the synthesis of van der Waals layer compound between phosphorus and sulfur. Here, things are a little bit opposite as in other compounds. Usually pressure facilitates novel compounds and so on. Here things are opposite, so let me explain. What is the motivation, first of all? First of all, I think a lot of people are kind of aware about molybdenum disulfide, a lot of applications, superconductivity, a very hot topic. And the idea here is that if we can have the same structure and same properties, but instead of transition metal dichalcogenides, like the case of the molybdenum disulfide, we can use main group elements like phosphorus that they are more abundant and cheaper. So one idea was to see what's happening with phosphorus. And at ambient conditions, as you may see, there are a lot of compounds stable between phosphorus and sulfur, different stoichiometries. However, they all share a common bonding. They all form this kind of diamantoid-like, if you like, or cage-like arrangement. Now, under pressure, the picture completely changed. Even at very low pressure, 10 GPa, only one compound is stable, the phosphorus sulfur 2. And the main difference is that instead of these molecular light arrangements, you have layers. You have more or less this structure, which is exactly the same structure with molybdenum disulfide. So one expects kind of the same properties since the structure is the same. And indeed, we managed to synthesize this compound at very low pressure and temperature. I was really happy with this project. It was the only project that every attempt was successful, so very easy synthesis. 10 GPa, 100 Kelvin, so easily accessible with large volume presses. And you may see here the X-ray diffraction and the comparison before the laser heating that we see only phosphorus and sulfur. And after laser heating that we can identify the new compound. And also the good thing with this material was that it was quenchable after completely releasing the pressure. And this was recently published in PRB. So there are ideas and there are ways to go beyond the established compounds. So I would like to finish my talk with a work in progress, a very recent paper we published, which in reality was control experiments, but attracted a lot of attention because of the subject. I don't want to pretend that I am the expert on batteries. I'm looking things on noble compounds. But according to my understanding in the fields of lithium-ion batteries and sodium-ion batteries, the main problem is that for the anode material at least, we need to find new materials. Graphite has a problem with the capacity, silicon with the expansion, and so on. And there is a lot of discussion in the field about phosphorus as one of the elements that can change the material with, from graphite or silicon, replace the graphite or silicon. Also in the case of sodium batteries, and a lot of people discuss about sodium batteries because sodium is much more abundant and inexpensive, neither graphite nor silicon are appropriate elements for materials for anode. So phosphorus looks like fits all, fits a new generation of lithium batteries and sodium batteries. And these are very recent theoretical predictions. This is under pressure for the lithium phosphorus system, predicting that lithium-rich compositions like lithium-5 are stable at 10 GPa, and this is the case for sodium. I don't know how clear it is, but sodium 5 phosphorus, this is at ambient conditions, is just above the convex Hull at ambient conditions. Another advantage with pressure, in addition to just synthesize the material and see what's happening, is that according again to theoretical predictions, pressure facilitates the increase of the alkali metals. So you can kind of mimic the procedure of sodiation or lithiation and see what are the intermediate structures. So we decided to look on this direction. At the beginning, try to see if pressure can really make a difference in this kind of compounds. Sorry, just to say that for some reason there are no experimental results in these systems. I think only 1 or 2 papers discussing the high pressure studies of lithium and phosphorus compounds without synthesis and so on. So it was a pristine field for us. And we started again very simply. Let's take lithium and phosphorus and see what's happening under pressure, just elements. Now, we managed to synthesize these compounds under pressure. Again, this was control experiments. Lithium-3 and sodium-3 phosphorus, and you may see here that can be easily understood. You can easily see it here from the X-ray diffraction, how the calculated diffraction pattern looks in the experimental pattern. Now, these compounds are stable at ambient, and one can synthesize at ambient conditions. However, the procedure to synthesize these compounds at ambient is extremely tedious. step heating, catalyst, and so on. I was really tired, but just reading the procedure, not doing the procedure. And in this case, at room temperature, without catalyst, we managed to synthesize these compounds. It's not novel compounds, but at least as a control experiment, now we know that pressure can really have an effect in this system. The pressure was really low, below 1 GPa. In reality, it was just the pressure Rowan needs to seal the duct inside the glove box to travel then at APS or ALS to do the experiment. We also try to see what's happening under pressure. We see a phase transition for both compounds from this layered-like structure towards an FCC structure. The pressure is about the same, both for the lithium and the sodium compound. We also try to synthesize lithium-rich and sodium-rich compound up to 20 GPa with laser heating, with constant temperature, and so on. As you may understand, doing laser heating with lithium is not very fun. A lot of diamonds failure, but at least we made some attempts. I mean, we failed, unfortunately. So there is something missing here. Maybe we need to examine again the theoretical predictions. Maybe we need to find new avenues. But at least looks like this system is promising about the role of pressure. And this was published recently in this Journal of Material Chemistry A. This is an SCS journal dedicated to battery materials. And the first author is an amazing undergraduate student, was an intern in Lawrence Liverpool National Lab. So I think it's time to finish. I don't have space and time to acknowledge and thank all my collaborators. So you will allow me just to show the logos of all the different institutions, universities that they were part of these results. And I will only take one more minute of your time to advertise this special issue that we recently launched. This is a special issue in the Applied Physics A, Materials by Design Under Pressure, Experiments and Theory, together with my co-editors. We would like to see new ideas, new papers, bridging the gap between experiments and theory. As you may see, the co-editors, we are 2 from experiment, 2 from theory, so we really understand and we acknowledge that there should be a synergy. I don't want to waste more of your time. The issue is open up to June 21. We understand this is a difficult time, so have enough time, and you are all welcome to submit papers. Just make sure that you select this specific issue. And I think it's about time to thank you a lot about your attention, especially during this difficult period with the COVID. And again, thank you very much, Ras and CDAC, for giving to all of us this opportunity to interact.
Thank you, Alice, for a beautiful talk. A lot of exciting results. That was excellent. Are there any questions for Alice? Just put them in the chat box or unmute yourself.
I think there is one, but
Hi, this is Rainy. A general question, so you put A and B in a diamond cell, you laser heat, and you get new peaks. That could mean a lot of things. As you showed in the very beginning, you have better stability of the single phases. You have change in stoichiometry. And one example that I sort of caught my eye was your results on carbon nitrogen. We spent a couple of years on this, and when you heat these mixtures, we found you make always diamond with a lot of nitrogen trapped. So we don't make a compound, we have a mixture. Yeah? So it's not a new material. And no matter what we do with carbon or the other, starting materials, whether it's graphite, glassy carbon, you make mixtures. So I think, when we did the cubic nitrogen or our first runs on silicon nitride, to look more closely, you take what you think you made and you measure the Raman shift, or you measure the compressibility by X-rays to see if you have a drastic change in these properties. So I'm a little bit, I think this is a little bit lacking in all this. You know, quick papers, new compounds is great. Most of it is probably okay, but the testing should be done a little bit more carefully in my eyes.
Okay, so first of all, okay, I was trying in the talk to present more aspects of the field, again, because all the results are published. So you are absolutely right that laser heating carbon is challenging, because we all know that most probably, not probably, you will synthesize diamond and then you are kind of trapped. And this was actually the main problem, and I think I made a comment about the problems we had. So whenever we had a conventional laser heating, we end up with diamond, and this was practically the end of the story, because then it was so stable that you cannot go forward. Also, it didn't couple with the IR and so on. So it looks like the only way to succeed, at least this is what we have done and we succeed, is to do the laser heating so fast that you will kind of trap the system in the case that you can melt carbon before it reaches the steady state of diamond, and we managed to reach the temperatures of 8,000 Kelvin or more. If we believe that during laser heating you can be accurate on this kind of levels. Now, of course, the characterization of the material was not only with X-rays. We have done Raman, which it was in perfect agreement with the Raman that you expect for carbon nitride. We also measured the equation of state of the material, which also the bulk modulus was in perfect agreement with what you expect for this compound. And as I mentioned, we managed to retrieve the material after removing it from the diamond anvil cell and measure the ADX, so measure the composition. I agree that ADX is not perfect for this kind of elements, but at least it was clear that we are looking for something one-to-one, and also that it's uniform. So I think we have more than enough evidence to claim that this material was synthesized. But I agree, and I think I tried to highlight this at the beginning, that this field is very difficult because you don't know a priori what you have synthesized. And we all know that the probing technique that you have available under in situ at least are very limited. So this is, I think, we need to acknowledge theory for giving us some tool to at least compare and have some support there. I don't know if you are happy with my response.
I'm very happy. Thank you.
Oh, as a follow-up to that, thanks for the question, Reini. That's a very interesting observation, Ellis. And you mentioned you measured the bulk modulus and you could recover it at ambient. Do you have enough material to measure the shear modulus? Because that's what correlates with the hardness, and the carbon nitride phases that we predicted many years ago all had relatively low shear moduli, although their bulk moduli were very high.
So this is usually the main confusion in the field. You see a lot of papers claiming that you have a high incompressibility, so this means high hardness, which is wrong as well. In this material, if you see the title of our paper, we try to be honest. We claim an incompressible material, and the reason was exactly what you mentioned, that we didn't have enough material to perform this kind of studies to measure the hardness. And the main reason for that, I think, is that the pressure that we need to synthesize was so high that you cannot go, at least at that moment, to a large volume press and synthesize enough material to do all this. So I agree with you that it was not a super hard material, it was an incompressible material, and the hardness needs to be examined in the future.
Oh, that sounds very promising though. Yeah, thanks. So Sasha from ARL has a question. Do you want to ask it?
Yes. I'm glad to attend your talk. What is your take on unstable according to sorry, you're not hearing me? Sasha? No, I think my microphone is, okay, no problem, Sasha, okay, so I understand, okay. So again, I don't want to comment about reaction barriers, this is your expertise. I think this is, if I understand correctly from your question, you're pointing towards my comment about diamond. Although it's not the most stable form, because the reaction barrier is high, it is stable, at least in our lifetime or more, right? So, and I think the bottom line here is that a lot of structures, and I think you're referring about methane and teflon, that they are stable. There are ways to trap them, the system in states that they are metastable. And I think this is something we all need to look in our quest, let's say, to synthesize new material, novel ways to stabilize phases. Now about the barriers and the calculations, I don't want to comment. I think you know much better than me.
Okay, thanks. More questions? You don't have
I have a question.
mic. Oh, go ahead. Yeah, Jim.
Jim Schilling. I mean, we all understand and appreciate that using high pressure can allow us to make materials with fantastic properties that wouldn't be possible or that aren't found at ambient pressure. But it's of course frustrating that let's say we have a 800-degree superconductor, and this if it were available at ambient pressure, this would revolutionize technology. But unfortunately, you take the pressure off and the superconductivity goes away. So I would think people working in this area, there would be as much work going on to make, predict new materials as there would be to bring forth ideas or to try to understand ways that one can retain these structures and properties at ambient pressure. Do you agree?
And I think this is why I started my talk saying that we need to look on metastability and low pressure. Ideally, you would like to have something that it is synthesized with large volume presses like diamond, let's say, or other ways, and it is stable at ambient. And you know, I mean, for instance, sorry for taking more of your time. Right now, to my understanding, diamonds, at least most of the weight of diamond, synthetic diamond, sorry, that you don't really care about very high quality, you care about the hardness also. My understanding is that they are made by detonation right now. So I think we can use high pressure because it's more controlled. I mean, when I say high pressure, I mean the DAC work or the large volume presses. And sooner or later, people will find a way. But I think if we really would like to move this field towards application, attract attention, and I would say in grants also, I think we need to think about low pressures and metastability. However, you can never decrease the pressure if you don't know what you expect. So for instance, I agree with you that the superconductivity at 200 GPa is not practical because you need to remove the pressure. When you remove the pressure, you don't have it. But if you don't know that you exist, you don't start to think about how to break it down. So just to make a parallel example, if there was not the study of the cubic gauge nitrogen, we would never think about how to break it down in pressure, synthesis, and metastability.
Okay, thank you.
So it's also a materials but by design question, which relates to Sasha's last point, calculating those barriers and validating that through experiment.
I was thinking, well, maybe you could add something to the, like one does in magnetism. If you want something that's a good permanent magnet, you throw a lot of junk in with it, with the magnetic materials to prevent the domains from moving. So maybe one could do something similar to superconductors to prevent, you don't want to mess up the good properties, but maybe you can prevent it from transforming back using some tricks.
Yeah, good idea. More questions? If not, thanks very much, Ellis. That was a great talk. Thank you all for joining us. And we'll see you in 2 weeks.
Thank you very much for
Thanks, Alice. Great talk.
Thank you, Alice.
Thank you.